Hello, Photoshop Junior. This is an assignment we're going to be using as part of our media computation, media manipulation theme to CS141. This is an assignment that I got from colleagues at Swarthmore College. I saw a presentation about it in the probably mid-2000s, and I've been using some version of it ever since. So learning goals, what are we trying to figure out? How are images represented by a computer? Pixels and pictures, which has to do with image representation. We'll look at flip horizontal, which will involve a return, once again, to our mirroring formula. So how's an image represented inside a computer? It turns out it's a grid of pixels, where each pixel is a tiny little square of color. So simple grid use really big pixels, or blocks of color, but an actual image is actually going to be much, much, much smaller pixels. So if you think about mosaic-style artwork, this is, here's the link to this. This is a mosaic picture they found online. It's actually a bunch of tiny little squares of different colors, and when you put them together, each individual square has a certain color, but you can kind of look at it and see the entire image sort of pop. And so you think of maybe museums or maybe outdoor art installations that are mosaic pictures. You've got lots of these tiny little mosaic tiles. They're making up some sort of an image. Turns out a computer represents a picture more or less the same way, but instead of using little colored tiles, it's using tiny little colored spots on the screen called pixels. So if you think about the Indonesian flag, in simple grid, it was, 18 squares tall, 36 squares wide. This gave us this kind of an image where each of our little blocks is actually fairly large. You can kind of see it and see the outline with the naked eye. That was our abstraction, our representation there. But if you think about what this actually is, this same image as an actual picture would be 450 pixels wide and 300 pixels tall. It would be much, much, much smaller, tiny little pixels that you can barely see in there, and you can't really see grid lines between them or anything like that. That's the smallest unit of color that the computer's capable of. So, here's a question. Head over to the Google Classroom. Well, actually, it's in Google Surveys. Head over and answer the questions about this. When a camera says it's 8 megapixel, what does that mean? Which of these answers best fits what we mean by 8 megapixels? Clearly, there are 8 huge pixels that, used by the NSA. No, I'm just kidding. It's not A. It's also not the case that cameras can only take pictures of cats. Total joke answers. This means that there's 8 million pixels in each image. So 8 megapixel, that's what it means. Mega tends to mean million. Sometimes it can mean 2 to the 20th, which is not exactly a million. It's, 2 to the 20th, a little bit more than a million, but whatever. It's pretty much the same thing. 8 million pixels is what we're getting at. So what is a pixel? Well, it's a tiny colored rectangle. So an image that has 600 by 800 resolution, that means it's got 480,000 pixels. So an 8 megapixel camera is going to have 8 million pixels per image. That may actually even be more pixels than we can represent on a typical screen, so that's why you don't really have that many 8 megapixel cameras floating around. Actually, I have no idea what megapixels cameras do these days. Maybe it is 8 million, who knows? I'm old. I remember the days of taking your film to get developed at the drugstore. Okay, so what color can a pixel be? We know these are colored pixels, but we don't really know what colors they are. Well, the possible range actually depends on the device displaying the pixel. It depends on the format of the image containing the pixel. There's actually a lot that goes into this. There's a lot of different standards. Sometimes you might see a little bit more resolution with one type of image format, a little bit less resolution with another. More resolution typically means that the images have to be bigger, so if you're sending them over the web, maybe you don't mind losing a little bit of precision, so there are definitely trade-offs. So for our purposes, for the lab that we're doing, and kind of in general, a pixel is going to have a red, green, and blue, or RGB component, and each of these values ranges from 0 to 255. So, how many unique color values are possible combining 0 to 255 for the red, green, and blue values? Go ahead and take a shot at that, see if you can figure this one out. Did you come up with 2 to the 24th? If so, you're correct. 256 values from 0 to 255, that's 2 to the 8th. And if you have that for red and then green and then blue, that gives you 2 to the 8th possibilities for red, times 2 to the 8th possibilities for green for each possible red, times 2 to the 8th possibilities for blue for each of the red, for each of the green. So that gives you 2 to the 24th total. A lot of images will also have what's another 8 bits for what's called an alpha channel, which is how transparent the image is. We're not actually going to use alpha channels, not really worry about that, so we're just focusing strictly on the red, green, and blue. That gives us 2 to the 24th possible values. Just to give you an idea, 2 to the 20th is about a million, 2 to the 4th is about 16, so that gives us about 16 million different unique color values for each pixel, which is a lot, and certainly, I don't know for sure if that's getting close to the limit of what the human eye can detect, but that's an awful lot of different colors. So, pixel in our next lab, it's going to be a new reference type with some very simple set of methods to get and set the colors of a pixel. So, for example, these are the pixel methods. We can get red, get green, and get blue, which returns an int. Now, the int values are only going to be between 0 and 255, but we're still using an int to represent it. And then we have set red, set green, and set blue. You give it an int for the red, green, and blue values. This doesn't have to return anything, because if you say, hey, set the red to, 50, it's just going to set the red to 50. We're not expecting to get anything back. So those are the 6 key methods for pixel. I should also mention, If you set a red value to something more than 255, like maybe you set it to 1,000, it's just going to cap it at 255. And if you set it to something below 0, it's just going to cap it at 0. So if you set red to negative 50, it'll just assume that you, for some reason, I don't know, thought you could use negative numbers, but you can't. It'll just set it to 0. That's sometimes called capping, or the more common term you'll hear is clamping, C-L-A-M-P, clamping. Okay, so what color would this pixel be? We set the red to 255, the green to 0, the blue to 255. What do we have? Go ahead and take a shot at this one. Hopefully you came up with purple. This pixel is going to be purple because we turn the red all the way up, we turn the blue all the way up. That gets us purple because red and blue together makes purple. Potentially you could say technically it's magenta or something like that. I don't know. I'm going to go with purple. So picture, pixel just tells us how to manipulate a single pixel, which is a tiny little square on the screen. A picture is a giant two-dimensional grid of these things, kind of like a giant simple grid. So if a picture is a grid of pixels, you can think of it as a huge simple grid. So what can we do with a picture? Well, we can get the width and height, which we could also do with a simple grid. We can get any pixel using its row-column coordinates, and we can set a new pixel into any valid location of our picture. So here are the methods and constructors we have for picture. This is our constructor. You give it a width and a height. It'll create a new image of that width and height. We can get the width and the height, which will come back as ints. We can get the pixel at a row and column, and it'll actually give us a reference to that pixel. We can set a pixel at a row and a column, given a pixel. No return value for that. And we can actually copy the entire picture. We're not really going to use this, but this is a method that's included. One of the buttons you have in your lab is a restore button if you want to get back to what the image originally looked like before you started testing out some of your filters for a particular run of the program, so you can give it a picture, and it will sort of copy this picture over the picture that you're currently invoking this method on. Okay, so what are you going to do? Well, we're going to write filters, little image filters, similar to Photoshop or Instagram filters, that will change or modify a picture in some interesting ways. So flips, mirrors, blurs, edge detection, different things like that. Converting to grayscale, what I call zombie vision, which really just means the inverse or negative of an image, and so on. So you're not going to be creating pictures from scratch. You're going to start with an image, and then you're going to go ahead and do some work to try to modify it. So what do we have? I'm going to demo it. So we're demoing flip horizontal, so you can imagine you have this lovely image. I can't find this. I found this on Flickr. I thought this was really cool a few years. This is probably like 10 years ago. And this would be the picture mirrored, so we sort of flipped it. So your BlueJ project will, that's not what I wanted. Right, it'll look something like this. There'll be two things. This has your main in it. This is what you'll right-click to run. This has all your filters in it. So if we open this up, you can see we've got some imports, including picture and pixel. That's good. These are names for your own buttons. You can add your own filters at the bottom. I'll show you where that goes. And then here's all the code for flip horizontal. Let's go ahead and test this out, and then we'll go through this code to kind of see what it does. There we go. So I'm going to go down here to main. I'm going to say, okay, let's run this. And it's going to pop up, and there's an images folder inside the BlueJ project. I've thrown some images in there. You can pick whichever ones you'd like. Let's go with Matt Berg, Knox CS major and honorary degree recipient from Knox a couple of years ago at graduation. There he is. He does some really interesting work. He lives in Kenya, and he does a lot of really interesting work doing essentially entrepreneurship in Africa. Really, really cool stuff. He was actually heavily involved in the IT side of Jeffrey Sachs' Millennium Village project back in, I guess that would have been like in the 2000s. Anyway, so here it is. Matt Berg, Knox CS major, receiving his honorary degree at graduation a couple years ago. We can flip this horizontally. We click that button. That's what happens. Boom. Check that out. We can do it again. Let's do it one more time. That was amazing. Cool. Suppose we flip it and do some other stuff to it, and we're like, hey, I want to get back to what this looked like originally. You click this restore button, it gets back to whatever the image looked like originally. And these are, you won't necessarily have these exact filters. I change the filters around each year, but these are some of the possible filters that you might be doing. Flip, vertical, zombie vision, grayscale, mirroring, things like that. None of these work right now because this is the lab that you would potentially be given. And then if you do something really cool and you want to save it, there's a little file option that'll like save the image that you came up with. Great, and then we can click quit, and that will end it. So that's what we're doing. Let's look at this first filter, kind of get an idea of what's going on. So first thing, we got to remember we're dealing with row column coordinates, not XY coordinates. So if you have a picture where the width is 6 and the height is 5, this is what the coordinates would look like. This would be 0, 0. This isn't X0, Y0. This is row 0, column 0. That's 0, 0. This is row 0, row 0, column 1, row 0, column 2, and so on, all the way up to 5, because 0 to 5 is 6, and the width is 6. The height is 5, so this would go all the way down. This would be 0, 1, 2, 3, 4, because the height is 5. So remember, it's row column coordinates, not XY coordinates, just like it was for Simple Grid. How do we find the mirrored pixel? That's really important for doing flipping horizontal. It'll also be important for flipping vertically and for mirroring vertically and horizontally. So if the image is W pixels wide and we're currently in column C, how would we mirror our current column to get the opposite column? Which of these formulas is going to work? Hopefully you came up with this last one, width minus 1 minus C. Sometimes you'll see this W minus C minus 1. They mean the same thing. Just, you can sort of look at it and realize it means the same thing. This is our mirroring formula, which we've seen a number of different times. We're going to use it again for this lab. So you can sort of imagine if we're 0, 0, that's going to mirror over to here. Well, if the width here is 6, if we're in column 0, and the width is 6, well, 6 minus 1 is 5, minus the current C value, or column value, which is 0, that's going to give us 5. 1 maps to 4, 2 maps to 3. We could kind of work through this to get an idea that that's what we're looking at. So this is the full code for horizontal flip. I don't like to keep writing picture.getWidth and picture.getHeight, so I tend to just copy-paste this for each one. I'll just set W and H at as local variables at the beginning of the function. And that way I can just say W over 2 and less than H and W minus, 1 minus C. I don't have to keep writing it. So let's think about what's happening here. So we're going through not every column, but half the columns. We're going up to W over 2. So we're doing half the width. And then for rows, we're going from 0 less than the height. And what are we doing? Well, we're taking the pixel from row column, then we're taking its partner, the mirrored version of it, from row mirrored column, and then we're taking pixel 2, which was the mirrored one, and we're putting it back to row column, and we're taking pixel 1, which is in the original row column place, and we're still keeping row, but we're mirroring the column. So we're basically picking these pixels up and then putting them back down in the opposite locations. And we're doing that for every possible pair of pixels and its partner. We're only doing W over 2, we're not doing less than W. And then we're returning the picture at the end of it. Now, you might think, hey, picture's a reference type. Can't we just make these changes to it, and then everything would be fine? Can't we just return void here? Why do we have to return picture? Well, we're not really returning the picture itself. You got to remember, we don't have like a magical reference to the stuff that's like in the video memory buffer of the computer and on the screen. We have a reference to a binary representation of some data that represents a picture image. So we do need to return the picture and then tell it to redraw for technical reasons. I'd be happy to sort of explain more about what's going on there. All these filters are going to be set up the same way, where you manipulate the picture, or possibly even create a new picture and manipulate that, and then at the end you return whatever picture you want, and it'll just go ahead and redraw that. Because if you're scaling up or scaling down, you're making the picture bigger or smaller. Well, we can't sort of take this picture and make it bigger or smaller. It doesn't have methods for that. We have to create a new picture that is in fact bigger or smaller to the dimensions that we would like. So this is just a walkthrough of everything I just said verbally. We're pulling out every pixel in its mirrored or inverse. We're putting it back into the opposite location, and that's what we've got. We'll do a bunch of clicker questions on this in class, and we will do this in lab for our next assignment. Thank you all for watching.